Application trend through planar 3 minimal and projective planar 2 minimal graphs. First author Volodymyr Petrenjuk and second author Dmytro Petrenjuk. First, the Centralukrainian National Technical University, Kropivnytskyj, Ukraine. The second, Viktor Mikhailovich Glushkov, Institute of Cybernetics of the National Academy of Science of Ukraine, Kyiv. Problem. Task. To demonstrate the possibilities of the phi method for the constructing of the set of all nonisomorphic 3 minimal planar simple graphs in which the set of all vertices is located on the boundaries of 3 true cells, and constructing the set of all nonisomorphic 2 minimal projective planar graphs in which the fixed set of points is located on the 2 boundaries, 2 cell or pseudo cells. Method of solving. The mathematical method phi transformation in which large structures are regarded as a set of small and simple substructures. For this, they may have some common parts that can be identified and amalgamated when constructing or reconstructing an entire structure from a finite number of substructures. First, an example of a possible application is the set of points placement problem or automatic control with subsequent success to each points. Second, if we talk about the surface as an almost infinite set of values of the function of several variables on a given finite subset as a set of vertices whose relationship between pairs of elements as a set of edges, we have an almost embedded graph in the surface. Third, if it is possible to set edges as an almost infinite subset of points, and in the absence of intersection of edges in the interior points of edges, we will have an almost exact embedding of the graph in the surface. Fourth, if the surface is spherical or resembles some extent a plane without holes, then use the following list of 3 minimal graphs to place on the boundaries of 3 cells of all vertices of the graph. 5. If the surface is a sphere with a hole or to some extent resembles a plane of holes, then we use the following list of 2 minimal projective planar graphs to place on the boundaries of 2 cells of a given set of vertices of the graph. Application 2. First, the structural properties of a complex system model presented in the form of a graph model can be studied using a symbol graph with a fixed set of points embedded in the surface on which the edges of the graph will be located, where surface is the Euclidean plane or projective plane. The point is as a vertex or the inner point of the graph of edges. These results will be useful in the systematic analysis of both graphs models and their topological aspect which will have common properties at the edges and several vertices of the graph model. The solution of our task was based on the method of graph transformation, whose founder is Mykola Pavlovich Fomenko, and the concepts he introduced. The recognizing of transformation of graph was taken from reference 1. Three minimal planar graphs and non-cylindrical graphs. According to reference 3, we will consider a simple graph to be a planar graph with having the following properties. First, two cells of the boundaries of which all vertices of the graph are located. 2. Removal of any edge of or its pinching into the point of this edge leads to the destruction of property 1. Second, according to reference 2, we define a non-cylindrical graph as a flat integrated graph having more than two cells of the cylindrical graph on their boundaries where all the vertices are located, whereas removal of any edge of graph or square in the point of this edge leads to the distribution of all the graph vertices on the borders of two cells of the cylindrical graph. Our problem is next. Let us study the identity of non-cylindrical and three minimal density planar graph and compare the graph from the given list with in figure 1 with the list on reference 2 and the modified algorithm of building of all three minimal planar graphs. We have the following relation for the planar graphs. Proposition 1. All graphs from the list in reference 4 are in the list in reference 2. Non-cylindrical and three minimal planar graphs are equivalent, and graphs theta and 6, theta and 7, k and 5, k and 3, 3 from the list in reference 2 are absent in the list in reference 4. The modification. We consider the modification of algorithm from reference 4 for constructing three minimal planar graphs, which was based on the inexact result of characterization of planar graphs with all significant edges with respect to the number of any auxiliary multiplicity of vertices equal to 3 at the operation of removing the remaining edge. The main idea is that such graph have at least one homomorphic graph subgraph and at most 3 such graphs. It is necessary to define the nature and possible variants of combining them. Terminal projective planar graphs. Task: to construct the set of all non-isomorphic two-planar projective planar graphs in which the fixed set of points is located on the two boundaries of two cells or pseudo cells. Similarly, of this task was the tasks for graphs with number of vertices less than 10 on various genus which solved in references 6, 7 and 8. We introduce a new characteristic that measures the substructure of the set X of points of graph on surface S. Proposition set 1. Each non-outer projective planar graphs with a given set of points that are not located on the boundaries of one, two cells or pseudo cell of an arbitrary graph abstraction of the projective plan can be represented as one subdivision graph K under 4 or a phi image of a pair of graphs homomorphic to graph from the set K under 5, K under 3, 3, K under 4, K under 2, 3, and K5 under 5 without edge. When identifying pair of points from the connection sets both in a path and in a cycle. Would you like to send your questions by email now, please? We will be very glad to prepare our answers for you as soon as possible.